All right, so we've got this system of equations, which we can write as this augmented matrix. And a couple of things to keep in mind here. If you look at this matrix one row at a time, what does each row represent? Like for instance, if we've got the row 3, 6, 1, negative 11, 9, what does that row mean, or what does that row represent? Yeah, each row represents one of the equations. So this second row could be thought of as representing just this second equation. Meanwhile, if we look at this by columns, what does each column represent? Like for instance, 2, 6, 4. Where do we get those numbers? Yeah, each column represents coefficients of one of the variables, except of course for the last column, which represents the numbers on the other side of the equation. And that actually provides an alternate way of writing this that can sometimes be useful. If you think of just the first column as a vector that's being multiplied by the variable a, the second column as a vector that's being multiplied by the variable b, third column as a vector being multiplied by the variable c, and the fourth column being multiplied by the variable d, those all added together have to add up to this final vector, 7, 9, negative 7. So an alternative way of thinking of this system of equations, instead of thinking of it as here's 3 surfaces and we want to know where those 3 surfaces meet, you could instead think of this as here's 4 vectors. We want to figure out what linear combination of those 4 vectors adds up to this result we want. We want to know how far do we have to go in the 1, 3, 2 direction. And then from there, how far do we have to go in the 2, 6, 4 direction? How far do we have to go in the negative 1, 1, 5 direction? And how far in the negative 1, negative 11, negative 16 direction to get to this location? So these are 2 alternate ways of thinking about essentially exactly the same problem. And the book calls these the column picture in the sense of if you visualize going some distance in this direction, some distance in this direction, and so on, to get to this location. We want to know just how many copies of each vector do we need, or what the textbook calls the row picture of the same system of equations. Row picture in the sense of thinking of each one of these as some surface on a graph. And in this case, it would be a 4-dimensional graph, so it's not really as visualizable. But 3 surfaces on some graph, and we want to know where do those surfaces intersect. And the A, B, C, D coordinates of where those surfaces intersect will be the same as the A, B, C, D coefficients that make these 4 vectors add up to this result. So they're depicting 2 different looking problems, but still representing the same solution, same system of equations. Any questions on that so far?
In order to set it up the way that you have it down, where you have column picture, let's say like the equations were like out of order to set it up, but I have to like put it in order by variable.
There just needs to be an order. So each individual equation needs to be ordered in the sense of something A plus something B plus something C plus something D. It doesn't really matter what order they're in as long as you choose an order and you stay consistent about it. Typically alphabetical order of the variables, but that's just a convention. The important thing is that all the equations be in the same standardized format. Like you wouldn't want to write one of them as having like some of the variables on one side and some of the variables on the other side. You want every one of these variables to be in the same format of something A plus something B plus something C plus something D equals something. Any other questions on that so far? So let's see if we can do the row reduction here. And keep in mind that we're basically solving both of these problems at once. We're solving the row picture question and we're solving the column picture question, since they're both really the same question. First of all, if we want to do just standard Gauss-Jordan elimination with row reduction or row operations, what's the first pivot we encounter here? The first leading entry?
1.
Yeah, in the first row, we trace from left to right. The first non-zero we encounter is this 1 here. And that's good. That's already a 1, so that's going to make the calculations easier. And we want to use that 1 as a tool to eliminate everything below it. So for example, what operation is going to use this row 1 to eliminate the 3 here? What can we add to row 2 to cancel out the 3?
-3 times row 1.
Yeah, we can add -3 times row 1. That'll cancel out the 3 here. And let's see what that turns into. 3 plus -3 times 1. Oh, first of all, I'm going to copy down row 1 because that's not changing. 3 plus -3 times 1 is 0. 6 plus -3 times 2 also happens to be 0, so that cancels out as well. 1 plus -3 times -1, that's 1 plus 3, so 4. -11, likewise, plus 3 is going to be -8. And 9 minus 21 is -12. So that's our new second row. Any questions on that so far? And have you seen the idea of an elimination matrix yet, or a transformation matrix? The idea of using a matrix to represent this operation?
It's not familiar to me. I don't know about anybody else.
The idea is, and this is going to be important as we go on through the idea of row operations, because each of these row operations we want to be able to represent in a very systematic way. The idea is we've got this matrix, and I'm just going to write the rows as variables. Let's say we call these R1 as a row vector, R2 as a row vector, and R3 as a row vector. The idea is we want to multiply this matrix by some transformation matrix so that the result is keeping R1 the same, but modifying R2 by adding -3 times R1. So R2 minus 3 times R1 as the new second row. And let's say we keep row 3 the same. So we want to make this new matrix, called an elimination matrix or an elementary transform matrix. Let's call that E for now, for elimination or elementary transform. Elementary in the sense that it's just doing one single operation to it. And we want to build a matrix that's going to result in this matrix turning into this matrix. And just, first of all, let's take a look at these size this needs to be. The original matrix was 3 by 5. The result, of course, we also want to be 3 by 5. So if we have, let's call this matrix A, and let's call this matrix B. Matrix A is 3 by 5. We want matrix B to also be 3 by 5. So what dimensions does our transformation matrix have to be in order to make this work?
Also 3 by 5?
3 by 5? The problem with that is, if this is 3 by 5, there's 5 things in this row. And we're going to combine these by combining a row of the first one and a column of the second one. So we have this times this, plus this times this, plus this times this. But then we have 2 more numbers here that don't work. So you can't actually multiply a 3 by 5 matrix times another 3 by 5 matrix. You run out of numbers. So what would this have to be instead? If you want to multiply 2 matrices together, let's say A, which is, let's say P by Q, times B, which is, let's say G by H. What has to be true about these 4 values, the dimensions, in order for this to even be possible?
Do they have to be the same dimensions?
The matrices themselves don't have to be the same dimensions. For instance, we tried multiplying a 3 by 5 times a 3 by 5, and that didn't work.
Right.
But specifically, which ones of these do have to be the same? Remember, the problem we ran into here is if this is 5 numbers in a row, and this is 3 numbers in a column, then we get first number times first number plus second number times second number plus third number times third number. But then there's 2 more numbers in this row that don't have any columns to anything in the column to match. So the problem is we need to have the row of the first matrix be the same number of things as a column of the second matrix. That is, the width of the first matrix has to match the height of the second matrix. So this width and this height must match. If the width of the first matrix and the height of the second matrix are not the same, then they cannot be multiplied. It just doesn't work. It's undefined, which means this is going to have to be something by 3. These inner dimensions matching up, that's what allows this to work in the first place. And the outer dimensions tell you the dimensions of the result. The matrix AB is going to be P by H. So the inner dimensions matching up tells you, yes, this really can be done. These can be multiplied. The outer dimensions, which don't have to be the same, tell you what the dimensions of the result will be. So in order for this to work, for E times A to even be possible, the inner dimensions have to match up. The outer dimensions are going to tell us the dimensions of the result. Since we still want the result to be 3 by 5, so we're going to have to make E 3 by something. That way, the outer dimensions tell you the dimensions of the result, 3 by 5. So in order to make this work, in order to turn a 3 by 5 matrix into another 3 by 5 matrix, we need to multiply specifically by a 3 by 3 matrix, a square matrix. Any questions on that so far? So to recap, you list a matrix's dimensions as height by width, height by width. The inner dimensions matching up means, yes, they can be multiplied. The outer dimensions don't have to match. The outer dimensions just tell you the dimensions of the result, the dimensions of that product. So let's see if we can build that matrix. If our goal is to take row 1 and leave it alone, take row 3 and leave it alone, but modify row 2 by adding -3 times row 1, most of these rows are not being changed. Row 1 and row 3 are not being changed at all. So let's start with the idea of not changing anything. What matrix can you always multiply by that doesn't change the result? What's a matrix multiplier that doesn't change what it's multiplied by?
Oh, would that be a 1?
Hmm?
Would that be a 1?
If it was just a number, you'd multiply by 1. So like the number 1 times a matrix is just that matrix itself. But what if you wanted to multiply by a whole matrix? What matrix multiplier, if we wanted to multiply A, which is 3 by 5, times some 3 by 3 matrix and get the same matrix A, what matrix will not change A at all?
Would it be the identity matrix?
Yeah, the whole point of the identity matrix is that it doesn't make any changes at all. Just ones on the main diagonal and zeros everywhere else. Because if we did that, if we filled this in, no changes, or making the identity matrix exactly as is, when we combine a row of the identity matrix and any column of this matrix, we're taking 1 times something from row 1 plus nothing. So we get something from row 1. And then combining, let's say, the first row and the second column. 1 times something from row 1 plus nothing is the same thing from row 1. So 1, 0, 0 really just means take 1 times something from row 1 and add nothing from rows 2 and 3. So 1, 0, 0 means keep row 1 exactly as is, don't add anything from row 2, don't add anything from row 3, which is exactly what we want. we want to keep row 1 exactly as is and not add anything from row 2 and 3. In fact, you could think of the first row of this transformation matrix as being a recipe for building row 1 of the result. This recipe tells you how much of row 1, how much of row 2, how much of row 3 to use. In this case, 1 times row 1, nothing from row 2, nothing from row 3. Likewise, the third row, 0, 0, 1. If you actually multiply this out, if you combine the third row with any column, you get 0 times something from row 1 plus 0 times something from row 2 plus 1 times something from row 3. The result is just that thing from row 3. And again, thinking of this in terms of instructions or a recipe, this is saying take 0 times the entirety of row 1 plus 0 times the entirety of row 2 plus 1 times row 3. In other words, keep row 3 exactly as it is. And that's exactly what we want to do. We want to keep row 1 exactly as it is. We want to keep row 3 exactly as it is. But we do want to modify row 2. So we're going to need to modify row 2 of the transformation matrix. And what operation do we want to do? How do we want to change row 2? Do we want to multiply row 2 by some scalar? What exactly do we want to do to change row 2 here? We're changing row 2 to what? What operation are we doing to it? If you look back to our original matrix, what change do we make to row 2?
Oh, we just subtracted the 3 times row 1.
Yeah, subtracting 3 times row 1. And note that we didn't multiply row 2 by anything. We just have 1 times row 2 plus negative 3 times row 1. So to write that in matrix form, we've got 1 times row 2. We want to add negative 3 times row 1. So I'm going to put a negative 3 here because we're taking negative 3 times row 1 plus 1 times row 2. And we don't want to involve row 3 at all. So I'm going to put a 0 here. And keep in mind, this still can be read as a set of instructions, a recipe. This is telling you how to build the new second row. It's saying take negative 3 times all of row 1 plus 1 times all of row 2 and no information from row 3. That's the new second row. Which means this whole thing, this square matrix 1, 0, 0, negative 3, 1, 0, 0, 0, 1, this is the elementary transform matrix that represents this step, or also called the elimination matrix. It's a matrix multiplier that represents the row operation we just did in the form of a matrix. You can also build this by taking the identity matrix and applying this transformation to it. Take the identity matrix and modify row 2 by adding negative 3 times row 1. The result is negative 3, 1, 0. So that's the elementary transform matrix. And note that it's exactly like the identity matrix, except for one modification, which represents the change that we just made. And this turns out to be a very useful way of keeping track of all the operations you've done to the matrix. Since each operation, each row operation, adding a row to another row or whatever, can be written as times a simple matrix, we can keep track of all those operations as just a chain of times this matrix, times this matrix, times this matrix, times this matrix. And then we can combine all those transformation matrices together to get one big transformation matrix representing the entire row operation, all the steps in one go. Any questions on that so far? And the notation that's usually used here, we would typically call this E sub something. E for elimination or elementary transform. Sometimes I see this called E sub 1, just because it's the first transformation matrix we're using. And then for the elementary transform matrix for the second step we do, the second row operation would be called E sub 2, and so on. Or sometimes they're labeled more specifically. Since we're using the second row first column, we call this E sub 2, 1. So that just labels which row, which column we're modifying. But either way, the important thing is being able to construct the matrix that's going to make that exact operation happen. You can multiply this matrix times the original matrix to get this new matrix with the operation already done. Any questions on that so far? All right, let's take a look at the next step then. Let me make a note up in the corner of the transformation matrix we just made. I'm just going to call this E1 to represent that it's the first one we're using. And also as an abbreviation, they often don't write in the zeros. If you've got a matrix with a lot of zeros, they often just leave the zeros as blank spots. So you might see this written as like this. One's on the main diagonal, a -3 here, and these blank spots are meant to imply zeros everywhere else. So let's take a look at the next operation we'll be doing. And we can kind of bundle these into the same step because we want to also use the same pivot to eliminate the other number under it. So what operation applied to row 3 would get rid of this 2? What could we add there?
That would be -2 times row 1.
Yeah. We can still use that same row 1 that we've been using. In fact, we want to use row 1 as a tool to apply to every row we need to for now. And -2 times row 1 will turn this 1 into a -2, which cancels out the 2 that's already there. So let's see what that becomes. 2 minus 2, 4 plus -2 times 2, that's 4 minus 4. 5 plus -2 times -1, that's 5 plus 2, so that's 7. -16 plus 2 is -14. And -7 minus 14 is -21. And we could represent this operation by a matrix as well in exactly the same sort of way. We could say that E2, the second elimination matrix we're using, we're going to be using something exactly like the identity matrix, except one small change. Specifically, what small change would we make to make -2 times row 1 added to row 3? Where would we put that extra -2?
Will we put that in the bottom left?
Yeah, bottom left, because we want to modify the third row. So we use the third row as the instructions. And for the third row, we want to take 1 times the third row exactly as is, no information from the second row, but we want to take -2 times the first row. So -2, 0, 1 should work here. That is -2 times the first row plus nothing from the second row plus the third row exactly as is. And that's exactly what we're doing. And again, we might just leave off the zeros as blank spots. So exactly like the identity matrix, but with a -2 here. And one of the really nice things about the elimination matrices is that since they represent just one single step, it's very easy to find the inverse. E2 inverse, for instance, E2 represented adding -2 times row 1 to row 3. If we wanted to reverse that, like let's say we've just done this step, but we realized that was a mistake and we want to back up. What would you do to undo that step? What's the opposite of adding -2 times row 1 to row 3?
Adding a +2 times row 1 to row 3.
Exactly. So that means we keep everything else the same, but instead of adding -2 times row 1 to row 3, we add +2 times row 1 to row 3. So finding the inverse of an elementary transform matrix is very easy. You just take that one small change and take the opposite of the number. Just multiply that one number by -1. So that makes it very easy to find the inverse. This is one of the big advantages of writing a large change as several elementary transform matrices combined together. Each one of those elementary transform matrices is really easy to invert. You've got essentially an undo button for each one of those. But let's continue the row reduction and see what happens. This pivot, this 1 is now alone in its column. We're good. What's our next pivot?
4.
Yeah, our next pivot, if we take a look at the second row, the first non-zero we encounter is this 4 here. So we want to use this 4 to eliminate everything above and below. That's going to take some kind of messy fractions here because we have to multiply the 4 by 1/4 to cancel out the -1. We have to multiply the 4 by -7/4 to cancel out the 7. But we can make this a little easier by manipulating the numbers. What do you notice about all the numbers in the second row?
They're divisible by 4.
Yeah, those are all divisible by 4. So let's reduce that by multiplying the entire row by 1/4. And we can do that. Multiplying a row by a scalar is one of the legal steps for row reduction. This is one of the row operations we're allowed to do. Because this is equivalent to, like, if you just took this equation and multiplied both sides by 1/4, that's legal. That is a step you can do algebraically. You can do the same operation to both sides. And that's exactly what we're doing here. This is equivalent to taking this equation, 0a plus 0b plus 4c minus 8d equals -12, and multiplying both sides of the equation by 1/4. So let's see what that gives us. This can also be written as a row operation, by the way. It's just a little different, or an elementary transform matrix. It's just a little different. We're not changing row 1. We're not changing row 3. But we are changing row 2. Are we combining row 2 with any other rows yet in this step?
Not yet.
Not yet. So we're not taking any information from row 1. We're not taking any information from row 3. We're just taking row 2 and doing what to it?
Multiply by 1/4.
Right, so we'll put a 1/4 right here. This row says nothing from row 1, 1/4 of row 2, and nothing from row 3. That's your new second row. So multiplying a row by a scalar can also be done by an elementary transform matrix. It looks exactly like the identity matrix, except with one of the 1s replaced with whatever scalar you're using. So that's how you would write an elementary transform matrix for that sort of operation, multiplying by a scalar. And also, while we're at it, in the same step, what could we multiply the third row by to make things a lot easier?
Oh, 1/7.
Yeah, those are all multiples of 7. So let's multiply the whole row by 1/7 and see what we get. Take this up here to get some more space. First row, we're not changing. Second row, we're multiplying everything by 1/4. The zeros stay exactly as they are. 4 becomes 1. 1/4 of -8 is -2. 1/4 of -12 would be -3. And then third row, the zeros stay as they are. 7 times 1/7, 1/7 of -14, 1/7 of -21. So that's our new matrix. And what do you notice about this matrix?
Row 2 and row 3 are the same.
Yeah, we've reduced it to the point where the second and third rows are exactly the same, which means in our next row reduction step, what's going to happen to row 3? If we try using this pivot to eliminate everything below it, what operation would take care of that? We could add what to row 3 here?
Row 2.
Row 2, although we want to cancel it out, so we'll need a negative.
Oh, negative row 2.
Yeah. But if we take 1 minus 1, -2 minus -2, -3 minus -3, what happens to row 3?
It's just straight zeros.
Yeah, row 3 becomes entirely zeros. And that's some important information there. If row 3 cancels out, that means the original row 3, in fact, all 3 original rows, if one of the rows completely cancels out, what does that tell us about the original 3 rows? If it's possible to use 2 of the rows to cancel out the third row, what does that tell you about those three rows? What terminology would we use for that? In general, if you can make some linear combination of the rows, we took some scalar times row 1, and you can think of those rows as row vectors. We added some scalar times row 2. We added some other scalar times row 3, and they all canceled out. They built the 0 vector when they were combined together in the right way. If you can get some linear combination of these rows to add up to the 0 vector, what do we call that? The terminology we generally use here, sorry, go ahead.
Oh, I was going to say I wasn't sure.
What we call this is linearly dependent. If it is possible to get these vectors, and we can think of each row as a vector here, if it's possible to get these row vectors to add up to the 0 vector by some linear combination, and that's all we're doing here. We're just taking some multiple of a row plus some multiple of another row plus some multiple of another row. Ultimately, we built this row of all zeros by just adding something times row 1 plus something times row 2 plus something times row 3. If it's possible to do that, if it's possible to get a linear combination of the vectors that adds up to the 0 vector without cheating and using 0 times row 1 plus 0 times row 2 plus 0 times row 3, because that's always possible. If it's possible to get them to add up to the 0 vector without using all zeros as coefficients, we say that these three vectors, in this case, these three rows, are linearly dependent. As opposed to if the only way to get this to work is by cheating and using 0, 0, and 0 as the coefficients, we would say that the vectors are linearly independent. And a very useful way of thinking about linearly dependent here is to think that linearly dependent means there's some redundancy, that some of these vectors weren't really needed. Like in this case, the fact that we're able to cancel out row 3 means row 3 was ultimately just providing information that rows 1 and 2 already had. It's possible to build a copy of row 3 just using rows 1 and 2 multiplied by some scalars and added together. Which means row 3 isn't really providing any new information. Row 1 provides some restrictions on the values of A, B, C, and D. A, B, C, and D can be any numbers as long as they make this equation true. Equation number 2 adds more restrictions, that 3A plus 6B plus C minus 11D has to add up to 9. That's a restriction on the values that A, B, C, and D could have. And that's a different restriction. These two equations represent different restrictions on the values of A, B, C, and D. Each extra restriction limits the number of possibilities. But the third equation, because we were able to get it all to cancel out, that ultimately means the third equation did not provide any new restrictions. Equation number 3 was just duplicating the restrictions that equations A and B, or equations 1 and 2 already had. Equation 3 doesn't introduce any new information, which means we can essentially ignore it. If we had just left out equation 3, we would get the same result because it was able to cancel out anyway. Any questions on the meaning of that so far?
Did that make row 3 linear dependent, or is like the whole?
The whole thing. Linear dependence or independence is a property of a collection of vectors, not just any one vector. So it's not really so much that equation 3 specifically is where the redundancy is. It's that this collection of three equations has some redundancy in it. If we remove equation number 3, then there's no redundancy anymore. But it might also be possible that if we removed, for instance, equation 2, then maybe equations 1 and 3 together have all the information. Or maybe if we got rid of equation 1, then maybe equations 2 and 3 have enough information. So it's not so much that equation 3 specifically is the problem. The problem is that we have too many equations. We have more equations than are really necessary in this case.
Gotcha.
Any other questions on that? All right, then let's finish up the row reduction. Row 2, we don't need to change because it's the pivot we're working with right now. But row 1, we also want to make sure that this pivot has zeros both below and above. So what operation can we do to row 1 to turn this -1 into a 0? What could we add to row 1?
Could we just add row 2?
Yeah, if we just add row 2 exactly as is, this +1 will cancel out the -1. And let's see what else we get. 1 plus 0 and 2 plus 0 don't change. -1 plus 1 cancels out exactly as we wanted it to. -1 plus -2 is -3. And 7 plus -3 is 4. So that's our new matrix. If we take a look at the pivots, first row, our first non-zero number is this 1 here. Second row, our first non-zero is this 1 here, so that's another pivot. Third row, everything's a 0, so there is no pivot in the third row. And now we check each of those columns with pivots. Each pivot is a 1. Each pivot is alone in its column, and the pivots are in order from top left towards bottom right. Any rows of all zeros are at the bottom. So this is in row reduced echelon format. That's really all you need to check, those 4 conditions. Every pivot is a 1. The pivots are alone in their columns, zeros everywhere above and below. The pivots are in order from top left to bottom right. You never have to backtrack. And any rows of all zeros are grouped together at the very bottom. So this is in row reduced echelon form. This is as reduced as we can get this matrix. We're done with all the row reduction steps. Any questions on that so far? So let's see what we can do with this. The fact that this didn't just turn into the identity matrix means we can't just read it off as like A equals 4, B equals -3, C equals something, D equals something. Instead, we're going to have to rewrite these rows as equations. But note that since the third row cancels out, we effectively have not a system of 3 equations, but effectively a system of just 2 equations with 4 unknowns. This is way too many unknowns and not enough restrictions, which means we can't narrow it down to one single point. We can't find one unique solution. Instead, we should expect infinitely many solutions. And if this were like a high school algebra problem, we would probably get to this point and say, there's infinitely many solutions, and that would be the end of it. But using this format, we can actually get more specific information about those infinitely many solutions and how they're related. And we can do that by writing out each row as an equation again. Because remember, those rows represented equations in the first place. We can take these rows and turn them back into equations. So for example, what would the first row look like as an equation? If we still think of this as like the A column and the B column and so on. How would you write that as an equation?
Would you have 1A plus 2B minus 3D equals 4?
Exactly. And then the second row as an equation?
That'll be 1C minus 2D.
Yeah, equals -3.
No, equals -3.
So we now have the original 3 equations with 4 unknowns reduced to 2 simpler equations with 4 unknowns. And the reason I say simpler is because we've reduced a lot of the coefficients to 1s and 0s. In particular, the requirement that the pivots be alone in their column means that some of the variables only show up in one equation. Like the A column has a pivot. And because of the requirements for row reduced echelon form, A shows up only in one equation. Likewise, C column has a pivot. So that's only showing up in one row. And therefore the variable C only shows up in one equation. Whereas the other variables, B and D, they don't have pivots, so there is no such restriction. B and D can appear in several equations. It so happens that B only shows up in one, but D shows up in 2 equations. The advantage of this is that it makes it much easier to solve for the variables that have pivots in those columns. And we call those the fixed variables. As opposed to the columns without pivots, which are called the free variables. So B and D, since they don't have pivots, would be free variables. And that's free in the sense that we are free to choose any value you want for them. You can just choose a value for B and choose a value for D, because B and D could be anything. But then once you've chosen values of B and D, that's forcing specific values for A and C. But we can get more useful information out of this by solving for A. And solving for C. And then B could be anything. So I'm just going to write B equals B. And D could be anything. So we'll just write D equals D. The advantage of this is that we can take our unknown vector with 4 variables, A, B, C, D, and rewrite it by using substitution. Every A can be replaced with negative 2B plus 3D plus 4. B, I'm just going to leave as it is, because it's a free variable. C can be replaced by negative 2D minus 3. And then D is a free variable, so I'll leave it as it is. So we're changing our unknown vector with 4 unknown variables into an unknown vector written in terms of only 2 unknown variables. We've reduced the unknowability. And even beyond that, we can split this up. We can look at this in terms of, if we look at just the terms of B, negative 2B, 1B, and then these third and fourth coordinates have no B at all. Then we can look at the vector of just the D values. We've got 3D. Second term has no D at all. Third term has a negative 2D. Fourth term has 1D. And then we also have a vector with some constants. We can split out the plus 4 plus 0 minus 3 plus 0. So the constants 4, 0, negative 3, 0. And now, since this vector has only B in it, we could factor out B. So we're left with negative 2, 1, 0, 0 times B. This vector has only D in it, so we can factor out D. 3, 0, negative 2, 1 times D. And we now have a general format for our solution. The solution consists of any vector of this format. So if you want a specific solution, you could just pick a value for B and a value for D. It could be any real numbers and add these up. That would give you a solution. What would be the easiest values to use for B and D? Easiest numbers to plug in. If you could multiply a vector by any number you want, what would be the easiest number to use?
1.
Even easier than 1.
0.
0. You could plug in 0 for B, 0 for D. These would drop out entirely. So 4, 0, negative 3, 0 should be a solution. If you plug in 4 for every A, 0 for every B, negative 3 for every C, and 0 for every D, it should make all these equations true. So this constant vector is a solution in its own right. But you can add to that any vector in this direction and or any vector in this direction to get more solutions. So we get infinitely many solutions since B and D could be any values. In fact, if you can think of this geometrically, this specific solution, 4, 0, negative 3, 0, is some point in 4-dimensional space. This vector is saying from that point, we can go as far as we want in this direction or its reverse. And this other vector is saying we can also go as far as we want in this direction or its reverse. So we end up with this 2-dimensional solution set. We can go from here as far as we want in this direction and or as far as we want in this direction, and that forms a plane. So the collection of all solutions is going to be a plane in 4-dimensional space. And you can describe that plane as this one vector plus any linear combination of these two vectors. Any other questions on that? That idea of the complete general solution to the system of equations. And of course, if you need just a specific solution, you can plug in any number you want for B, any number you want for D. 0 and 0 would be the easiest, of course, but any numbers will work. So you can build more solutions, as many solutions as you need, just by using other values of B and D. Any other questions on that? All right, if you want to get some more practice on this, try this approach out for other system of equations. You can find more systems of equations in the textbook, or even if you just look up online algebra, like high school algebra practice problems for systems of equations, but try this new approach on those old problems. Good way to get some extra practice. Feel free to email me if you have any other questions, and I will see you next time.